Wow, I feel like Ian should be giving this talk, actually. That was an amazing, very generous introduction. And thank you also, Nate, and to everyone in the forum for coming out in the rain and for all your hospitality. I've had a great day so far. I want to talk a little bit about our work and kind of zoom in on this question of research in design, innovation, and really how you fold that into a professional practice of architecture. I have some new work that I'm going to show you that I haven't shown anyone before, so I'm excited about that. Nate did put the fear of God in me about timing, so I'm bringing my watch here. But we got a late start, so you owe me 10 minutes. This is a sort of an inspirational image for me. I remember as a kid seeing this image from, I think, 1973. It has a particular name. It's actually called the blue marble. And it's this image of Earth, one of the first that came from one of the Apollo space missions. And, you look at this thing, and this image, this picture is 40 years old. You can tell it's an old picture with all the kind of funny NASA stuff that they have around it. But it's pretty shocking because we see how finite the world is. It's this chunk of material and surrounded by space, and it has these clear borders, which is sort of one planet, and we're living on it. And at the same time, as architects and as designers, interior designers, landscape architects, we're confronted every day with so much standardization, so many given things that have standard shapes, standard dimensions, forms, and also just habits of mind, standardized ways that we think about things that seem like they're given. But of course, they're not really given. They're constructed, over time through history. So how do we work with new materials? How do we think about innovation when we live on and work on a bounded planet, and we're within such a strong kind of mechanism of commerce and capitalism and liability and everything else that we're all very familiar with in many walks of life, including architecture. I don't pretend to have the answer to that question, but I do think it's a very important question for people to ask. And I want to talk real quick about three aspects of our studio at KVA MATx. We do try to think in this way, right? We do try to see the world in a slightly different way, whereby everything that's nature, everything that's architecture in the built environment, and everything that's technology is really just a single system. And so you might say, well, okay, that seems pretty straightforward. That's not such a hard act of the imagination. But it gets a little tricky because, if everything's the same, then there's no real difference fundamentally, because it's all one planet, between that which you call city and that which you call country or nature. And then when you have stuff that you want to throw out, right, you're using something and you're done with it and you want to throw it out, there's no away, right? There's no place that's sort of out of the picture that's a way that we can put things anymore because we're sort of living in this one condition. And architecture is not any different than nature, and that's kind of a hard idea to wrap the mind around. But that's kind of the theme for the group of projects that I'd like to talk about. So we've set up, I'm kind of taking the lid off of our studio. We work in a brick box, a little warehouse that we bought. And we have a number of different resources that we use, workshops. We have an open studio where everybody can hear everyone else talking on the phone. We have a little optoelectronics lab, places to put our full-scale mock-ups. So we've constructed a place of work that allows us to do the work that we want to do. And then, of course, we have people. These are all the people who've been involved in the 6 projects that I'm going to show you tonight. So we've constructed a particular kind of place to do our work, and we work with a great bunch of people. So I want to jump into the first project. It's actually a project that does take place in Paris, as you say, but also slightly to the north, Lille, which is another French city. And it has a French name because it's a French project, and the French name is Climalin, which is kind of a triple pun. It means climate, and it means linen, the material, and it also means malin, which means street smart in French. So it's kind of an environmental, kind of street smart linen material project. So one of the things that is crazy about nature is that it is so shocking. I mean, it's just wild. And this is a field of flax, and you know that linen comes from flax. And one day every year, a whole field can just go to flower like this. And so the whole field, which was brown, suddenly becomes blue, and it's pretty amazing. And in Lille, there's a very particular kind of flax, which produces the best linen in the world. And our client is a small-scale linen manufacturer who's been doing this for many generations. He's in the blue there. His name is Olivier Ducatillon. And so he's a master weaver, and all of his machines are analog Dobie looms that you see here in these pictures. These kind of like really old machines from the kind of World War I era. And when Olivier and his company came to us, he said, we want to partner with Bouchara, who's a distributor of textiles, and we want you to make an electric textile with linen. And we said, well, what can linen really do, and does that make sense? Perhaps not. So we started to think about how linen, this very absorptive material, when in summer you can wear linen because it absorbs your sweat and it's very comfortable. And what we started to think about, it's a little hard to see here, is different sources of heat in the domestic environment. Radiators, car seats that warm up when you sit on them, servers from for your computer, light bulbs, etc. Everything, laptops, lights, things like this that are putting out heat. And we got the idea that maybe the linen could hold heat and then give it back later. Maybe it could borrow heat and cooling that was sort of wasted in the ambient atmosphere and give it back to the wearer. So together with another French company called Winco, we developed a thirsty linen that has a phase-changing material in it. And that phase-changing material is the white material that you see there that was coated on. We eventually got it within the linen thread, and that's made out of vegetable oil. So you have a 100% natural phase-changing material that can absorb heat and cooling, and you have a 100% natural organic linen, and you're putting them together in a different way. And that interests us. And we call that kind of the supernatural, when you take things that are completely natural, but you pair them together in new ways, and things that are also super old, like linen, and kind of new, like phase-changing materials. So then we used a software, which is not really used by architects. It's called Poincaré. It's a textile weaving software so that we could weave certain strands right into the linen, and we could organize those strands in patterns. And we wove in a color-changing, thermochromic color-changing thread into this. And this is, we did a number of projects. I'm just showing you one, the scarf. So the sort of process begins where you take your Climalin scarf and you toss it on the radiator. If you're living in France, you have these radiators that are kind of on low all the time. They're efficient, kind of radiant heating. And over time, the fabric itself will begin to get warm. And as it begins to get warm, a pattern emerges within the linen fabric. A pattern which could remind you of the flax fields, which could remind you of the row of linen. And that is telling you that the linen has absorbed heat. This is Davis actually modeling one of the first scarves. And what we liked about it was that this was a linen that could be mass-produced, on the Dobie looms. But every time you wore it, you could make your own heat signature. You could make your own kind of pattern in the cloth, and you could change that. I don't know. JD, whether we can make that any sharper. Certainly a lot sharper on my computer, maybe not. And then when you're hot, like for example on the bicycle, you get much more of a pattern. So that's the idea about taking two things in nature, taking an ancient technique, taking an emergent new kind of technology, if you will, even though it's really just nature. It's not a technology. Phase changing is nature. An ice cube is phase changing, and bringing them together. So we try to bring, and what I'm going to do is sort of pair back and forth what you might call research and what you might call architecture, and then I'm going to get you all confused, and you're not going to know what is research and what is architecture, and that will be the moment of victory. This is the Tauser Anthropology building, and this is a project that we completed recently. It brought together a number of interdisciplinary social anthropologists and archaeology people and people who study the Mayan culture, brought them together in one building. And we were interested in a very old-fashioned, old ancient technique and material, brick, and in this idea of kind of corbelling, and not just a kind of corbel of a header brick over a window, but really a spatial kind of corbelling, as you see here in this example. So the project started out, as kind of like one of these, this could be a tough project to do, because we were asked to reuse this building here. And this is right next to a very important historic landmark building on campus, which is the Peabody Museum. And so this sort of minor modernist building, which was built in 1978, had all sorts of problems. It didn't meet code, it didn't meet energy code, it didn't meet handicap accessibility code, and it had no entry. This was just kind of a void. And worse, it had mold all within the walls, so it was a bit of a disaster. And so our task was to reuse all of the structure of this building. That means all of the columns, all of the concrete slabs, even the fire stairs, all of the foundations, and all of the utility tie-ins. And we were asked to add 2 more floors onto this building. So we go from this to this, and that's really quite a transformation. So we tried to, in this project, you can actually still see the concrete slabs. These are where these little windows are hanging off of, and we're using actually a standard light here, but it looks like structural glass because we're popping it off the face of the brick just a little bit, and then making a kind of large Mayan-like entrance and really trying to give a front door to this department because they were very, very proud of their curriculum, and they really wanted an address on Divinity Avenue. So I'm going to talk mostly about how we worked out the digital brick in this kind of giant corbel, a giant corbel with no expansion joints. So we started with the idea of a door and its dimensions, the front door of this building. And there was a zone which we could work in. There was a limit to that zone. And as we tweaked in our software, as we tweaked and masked the building, it would automatically generate a set of bricks. I think you can see it a little bit better here. So what was interesting was instead of taking one brick at a time and sort of aggregating those bricks, we developed a surface and then a piece of code that would organize bricks according to the form of that surface. And so that meant that we could have a hung brick wall and have that be authentic to the actual form rather than being just applied. So we realized we were kind of in trouble with this brickwork. It was all very fine and well on the computer, but we realized we had to reach out to our local masons, and so these guys are kind of look tough. This is the Boston Mafia, and our local bricklayers union. But they proved to be really invaluable on this project, and we've developed a very close alliance actually with this particular union. So we would generate these drawings and diagrams that I tried to show you on the big screen. And what they would do is produce these dry stacks, which are relatively quick for them to do because there's no mortar, so the bricks come apart easily. And they would test the various different stackings that the computer was generating, and then we would work with them and look at them, and we could kind of understand what we were getting, and we could work on a workflow from the digital to the analog to the digital to the analog. So it was actually that kind of really cold winter that we had, we became quite fascinated with we're using a wire cut brick here, so it's very crisp edges, and we became very fascinated with the repetition of this brick. It's like always the same thing, and the way that it also just creates these fields, and that at the edges, the bricks form a unique pattern, which is absolutely to do with this spatial inflection, at the front door. So there won't be a quiz afterwards or anything, but architectural drawings are important. We do all of our own working drawings, which are the instructions for building. And people were looking at this building, they were saying, this is so odd, you don't have expansion joints, how did you do that? And people were like, oh, a brick building without expansion joints, that's interesting, we like it. And so I think this is kind of the new opacity. I mean, I realize I'm saying this in a town that's built on steel and glass, but it might be time to expand our repertoire of building materials to include mud, mud, dirt, and brick. So there's also, this is a top view of the building in model, and we also have this kind of door, if you will, to the sky right here. And that is a very large light well that brings light, of course, all the way down into the building, and it kind of unwinds like an orange peel inside this project, engaging the corridors and kind of organizing everything around the building. So we have a number of kind of photographic collections from the Tozzer archaeology collections. And then we organize this so that both the subjects of anthropology, the people who anthropologists are studying, and the anthropologists themselves, and the people are kind of mixed up as they go around the corridor. So that's producing a good bit of productive confusion about who's the expert and who's being studied. These images are really looking a little blown out, and I'm so sorry because I'm enjoying it really nicely on my screen. Okay. This is the secret space, that light well space inside the building. This is the light well, and it's made up of a number of panels, birch plywood panels, and I want to talk a little bit about those. What we did was we took all of those panels and we kind of spread them out. And with our acoustician, we tried to figure out regions, which we're not going to see well here, but regions like up here or over there or down along here where we want acoustic absorption. And then we figured out regions where the light was going to hit across all seasons, and we wanted reflectivity there. So basically we wanted to create a kind of a hybrid material, a hybrid wood material. And we loved the original birch bark, but unfortunately when you get birch plywood, they take the bark off the wood and they give you a kind of a homogeneous yellow wood. So we wanted to introduce striations that could reflect light and material that could absorb light. So we made a birch rhino scripting, grasshopper script here that made the birch panels all unique. And then with a tool like this, we could take each birch panel, and you see one here being fabricated right here. The panels could be put here, and then we cut grooves in those, and we can then populate those grooves with different pieces of reflective, plane mirror, or acoustic absorbing material. So you can get the sense a little bit that there's light that's reflecting at the top and sound that's being absorbed in between. And that's just another view of the building. And I want to show you another project which I haven't shown before. Just recently opened, and this is the Institute for Data Science. It's called Wegmans Hall at the University of Rochester. Interdisciplinary labs that come together to study data, to study big data and how that's influencing the sciences. So I want to just sort of, this is also a brick project. And Rochester is the snow capital of the world, of New England at any rate. And instead of carving in, what we tried to do is stick bricks out in this project. Stick bricks out and let the amount that they come off the facade be related to the overall geometry of the building. So Let me tell you the whole story first. This is a lab building that we did, pretty complex program. It fronts onto the engineering quad and tries to complete that quad by turning both to the quad and, as you can see here, turning slightly away, breaking its geometry, and turning towards the Genovese River, which is just right here. So you can kind of see that in the site plan here, ground floor site plan. There's one geometry which relates to the sciences quad, and then the other one which relates to this natural system, this river that you can see right here. So, you know, we started out with like the dumbest box in the world because this building had to be pretty affordable. We broke that box to the two geometries. We inserted a kind of public set of spaces in the middle. You can see people are running up and down this building, and then we introduced some two-story spaces on either end, and that's basically the organization of the project in a nutshell. So here you can see the very hairy brick that's beginning to happen here at the most extreme part of the building's turning, when it's cranked the most off of the campus grid. And this, of course, begins to reflect not only snow, but natural data of light, daily light and seasonal light moving across that envelope. The ground floor has the Institute for Data Sciences. It has an auditorium here and a circulation path that moves up a main stair and crosses back over and eventually comes up to the top of the building here, and I'll show you that real quick. We like to make these kind of clunky, simple cardboard models that just show us the public sequence. So you can see here the ascent up, the main stair, which is here, coming up, moving up into the double-story space that then looks back across the quad. And data, the binary 0-1, became a kind of a way of tying all of the interiors together, the auditorium here, the circulation, which is sized for collaboration. This is actually a robotics crit happening up in the top space. It's nice to see that building for us completed. The next project I want to talk about is the Soft House. This is a live-work residential development in Germany. We did this as a joint public-private venture with the Federal Republic of Germany and also Patrizia, who's a real estate housing developer. And this project actually started out really as an idea, a very just small idea about with a question, how could we radicalize domestic infrastructure, right? How could we rethink about how you get electricity and light in a house? And so we actually initiated this model. We made a model in the office, and we said, let's take this very old technology, which is called a curtain, and then this technology here, which is called a curtain track, and let's ask those technologies to do a different job. Let's ask those technologies to harvest energy and give light. And so we imagined a house where, as you could move the curtains in plan here, you could create different kinds of rooms and figures. And, you know, we had a lot of fun with this. We put our people in, and they're having a party here. And, you know, that was the Soft House. That was an idea that we had. And we didn't think that much about it. But a short while later, we got an invitation from the International International Building Exhibition, IBA, International Baustellung, which is a venerable German tradition where architects from around the world compete, and those who win get to build a housing project that then gets lived in. So it's a kind of a test of new ideas. And the challenge in just south of Hamburg was in this district, and it was to try to think about a new lifestyle that would be sustainable and also be a passive house, which is quite challenging because the German codes for passive houses are difficult. So we We came up with a very simple massing. We have to transform the idea because this is a live work. So this podium here is all the offices and working components. This is residential here. And we began to think about a fabric that could twist to the east, to the south, and to the west, and like a sunflower move and kind of follow the path of the sun to collect energy and charge, provide electricity in the house, charge things in the house. So this is the built project. These are the flexible solar materials here. We call these twisters because they twist like a sunflower. They move, the house faces due south, and these move from the east to the west during the day. You can come in through the garden. You can scoot up one of these ladders to a terrace, and there's also a e-vehicle entrance, parking entrance on the back. So after we won, we were extremely excited. And then, you get this feeling as an architect, as a principal, you're like, boy, now we are mandated by the government to build this. And we have to create 3 new technologies that we've committed to. The twisters, the curtains that bring LED light into the house, and also we're going to make this house entirely constructed out of solid wood. So we had a great team, but this was really challenging stuff. And you see here my colleague, an engineer, Jan Nippers, who was sort of bravely smiling as he stands before the Steiner wind tunnel test, trying to test the twisters, because this isn't really pretend anymore. People are going to be living here. It has to meet all German building codes and be qualified as a passive house. And so we thought about what kind of wood to use, and we decided to use a local technique that's a very old technique, actually it dates back to the 12th century, of doweling together planks of wood. So you take basically a hardwood dowel and you put it into a bunch of fast-growing softwood, fir in this case, and there's a kind of biometric fit. This dowel has less moisture than this, and so they lock together. And any small-scale manufacturer can make these panels. These are the 4 units about to be trucked to the site. We worked with Merkel Holzbau, a small company about 20 kilometers away from the site. And then these panels are erected to create our solid wood construction. So that means no glue, no hardware, no nails, no brackets, and when the house is when at the end of its life, it can be completely recycled. So it's a very different approach to building. This is the back. We use sheep's wool insulation. The green paper is the building paper. It's a product made by Serge Ferrari. And then we put just a rain screen of larch wood, which is pretty typical in northern Germany in that area. And this is the back of the soft house. The green windows are actually panels that slide because the Germans have very strict acoustic codes. So onto a parking lot and a small street like that, you need to be able to close off all the bedrooms from sound. And then these are the e-vehicle garage doors and entries there. So now I want to take you inside the house and talk a little bit about the curtain system. So we have very simple architectural partie, this kind of very simple 2-story residential component, and then working below with the twisters. And it's really almost like a shoebox, very simple, all wood interior. And we wanted to use the power from the curtains to drive in part LED lights. So this box here is taking power from the twisters, bringing it along the curtain track, and bringing that into this curtain. And of course, those curtains can move back and forth. So they become, the kind of important aesthetic signature within this very, very simple, super simple massing project. And you can kind of, every curtain pulls into a little round figure. And those little round figures in plan actually are little microclimates. You can see them kind of moving here. It's always a little bit warmer because the curtain reflects heat from the floor and heat from your body. This is also a very old-fashioned idea. The King of France actually used to have around his bed a curtain, just to keep warmth in. So here you see the twisters, and you can see the curtain I'll try to show you. I'll try to show you this movie. This was a Swiss television, Swedish television. I don't know why that birdhouse is there, but I'm the architect. I don't live there anymore. So anyway, I don't know any of these people, but Swedish television came and visited them and interviewed them about the Soft House. Everybody is living in the Soft House now. They moved their kitchen downstairs, so they are working actually upstairs. And this shows how they're using these curtains, which are actually made in Sweden through our manufacturing consortium that we set up for this project. And you can see how it moves from the wall to this kind of little round figure and ultimately around through the bed. And this is actually what the Soft House looks like just last summer when I was visiting there. It's gotten a little bit woollier. People have put a lot more plants on the terrace, but I kind of like that. So in the next segment of projects, I want to talk about this idea of the predicament that we're in, the good predicament that we're in if architecture and nature are the same thing. If architecture and nature are the same thing, then how do we give voice to our partners in architecture, natural forces? And I don't necessarily mean, wind, sun, water as resources that we're going to extract and kind of use, for our own profit, but how can they become a partner in architecture? So how do you give voice, for example, to a river? So this is a project that we did for a public ferry terminal in Manhattan. This is a public project, so those of you who are architects know not easy. We had a three-headed client, public client, New York Economic Development Corporation, the Department of Transportation, DOT, and Parks working on this project. And so the public ferry terminal actually turned out to be quite an important real estate catalyst in this area, around East 34th Street. There's been a lot of new development, and it does help to have water-based transportation, not only for safety, but just to give a presence and a character to this part of the city that's so close to the river. It's close to the river, but not everybody understands that the East River is actually not a river. It's an estuary. So it moves twice a day up here and into the estuary, and then it moves down into Long Island Sound. So it's a tidal estuary, and that movement is super important to keeping all of the fresh water in New York City clean. So we wanted to not just content ourselves with traveling around on the surface of this water, but to try to understand what was going on below the water. And we did that through the idea of reflection and through the idea of sensing. So New York has all these satellites revolving around it. It just does. They were there, and they're in orbit, and they're still working, but nobody uses them anymore since World War II. So we decided to it's not every project that has leftover satellites in it, but we decided to try to amortize that digital layer in the city for public good. So we imagined how we could use all of that data from the satellites for real-time passenger messaging, for commuters so that they could work while they were on the ferry, for wayfinding, and for emergency escape off the island, like in 911, and all of that kind of stuff. So we, oh my goodness, I am so sorry. I've never seen this happen. But imagine, if you will, a fantastic diagram showing you exactly how this project works. I'll describe it to you this way. At any rate, so the water is, let's imagine that the water is moving here, which it is. The water is moving, and as the water moves, so do these lights change. They actually change direction and they change color, so that over time, as you're commuting back and forth on the ferry, you begin to understand something about the tidal flows of this river, and the whole canopy of this project becomes a kind of a passive or an environmental sensor that's sensing the tidal flows and movement. This is a project that we had to sort of build in literally a couple of weeks. So we used a system that was prefabricated. We used a super simple CMU concrete block structure here for ticketing. And then we really limited the steel, with Michael Stein, our engineer, we developed a tensile fabric system that wraps around here. And then these are the skylights, which will have the LEDs. And all of that got made off-site, and the building got kind of dressed, it got wrapped. And then finally, the tension rings are put in, and the LEDs are put into these skylights. So that's happening with the LED light. And what we wanted to do was sort of take advantage of this effect, which is called the caustic net effect. And you probably know this from swimming pools or from canoeing under a bridge or something. But this is the refracted light from water. And we wanted to capture this on our aluminum surface. So all of the panels were made in a shop where they could be made with better quality and they could be made without dealing with weather. And then they're all numbered and they're assembled in mock-ups like this. And you can begin actually to see some of the moire effects that are beginning to happen because this is a double layer of perforated aluminum. And then in the ferry station itself, you can, even with a still photograph, this is not photoshopped or anything. This is the effect of looking through two layers from this vantage point. And you can see the LEDs here and also the kind of interesting toroidal form that begins to connect the bottom layer of the roof canopy with the top layer of the roof canopy. It's a multimodal station, and it's been great. It's been super popular for people. So if you're visiting Manhattan and you're coming in from LaGuardia, you should take the ferry. The next project is also a river project, but a very different kind of river. This is the Amazon River. And this is the Portable Light Project, or in Brazil, it's called Luz Portátil Brasil, which just means Portable Light Project. This is a small NGO that we run out of our practice, and the Swiss Journal ranked us, I think, 93rd out of 100 NGOs in the world. Yay! We're very happy about that. They're based in Geneva, and they're Swiss, so they're very serious about that. So what we do is work with a different kind of solar material, which is flexible, that you can see here, and this is manufactured by Global Solar, a company, but we've partnered with them and developed wiring so that we can get a big panel and then just cut it in half and produce 4 panels. And at first Global Solar didn't like that because they thought that was a little bit like cheating, like you buy 1 panel but you're actually getting 4. But in the end, they came to understand the benefits of it. So this is a long project, and there are many different portable lights. So I will just show you kind of early instantiation of this project when we were working in the Mexican Sierra, the high mountains and underserved communities in the Sierra. And this young woman, Alina, is putting together one of the first portable light kits. You'll notice it has 2 panels. Those are the dark things there. She's pulling a string which makes the textile pop into shape, and she's going to turn it on there, and she has a mobile office. She can do 2 things. She can collect energy, have light, renewable light, and she can charge a cell phone, and that's it. So that's everything that portable light does. It charges a cell phone, and it provides renewable light. So in Brazil, we had some great partners. We worked with the Inter-American Development Bank. We worked with a fantastic NGO, and we worked mostly on these 2 rivers. This is actually the mouth of the Amazon, and this is the Tabajos River here and the Arapontes River here, and down here is Sao Paulo and Rio. And this is just our logo for Luz Portátil Brasil. So first thing we had to do was, value engineer, get rid of a solar panel. So we bucked and boosted the circuit. We pulled in some expertise from Linear Tech, which is a semiconductor chip manufacturing company. We did that so that we had this very simple kit, which is here in white. It has a big red button, on and off. It's a hold-down button, so you don't accidentally turn it on and off, but it's super simple. Inside here is a small battery from a cell phone. You can plug in your solar panel, you can plug in your LED, which is here. We developed our own little heat sink, so that's nice. And then you can charge a cell phone, and that's the kit. So that kit then can take many different forms. And what we discovered was that if we could slip the kit into a piece of reflective textile, the LED light would be bounced around, and that creates a much better light to read by and to work by, because an LED is a point source. And anyone who's ever been camping and had an LED headlight, you know what that's like when you look up, you go like, yes, and then your headlight's looking right in someone's eye. So this reflects the light, and you can see that this element is actually right here bouncing all this light in this textile. What is this mysterious textile, you might ask? It's nothing other than duct thermal insulation, which is pennies a meter, a square meter. So it's a kind of architecture material that we took from architecture and that we bring to this project. So we worked with our NGO from Santarém, and I don't want to go too long, but basically this picture shows you something is wrong. This area is rapidly urbanizing. There are all sorts of materials here: kerosene, styrofoam, gasoline that should not be here in this community, and that there's no way to dispose of these things. So basically what the Portable Light Project in Brazil is trying to do is to get rid of this kerosene light, which is bad for people and bad for water, bad for the river, and replace it with this light, which can be carried, folded up into a lantern shape, and used. And we have an ambitious plan with our partners to move from an east-west global shipping model to more of a north-south America's shipping and manufacturing model. Because right now, if you get a solar product, if you get a small solar flashlight or something like that, it's probably going to come from China or India. And Brazil trades a lot with China and also with India, the BRIC countries, you may have heard. And so all this stuff is shipped that uses a ton of fuel, a ton of carbon, and then these kind of really cheap devices break after 1 or 2 years. And that's a big problem, because the energy that it takes to make the silicon in these hard glass solar cells, you need to run the cell for at least 2 years before you get clean energy back. That's a complicated equation, but it is a predicament. So what we tried to do was to connect the users, the maker communities, with the user communities. And this is the first project that I'm aware of in South America that does do this. So we had all the textiles for the 13 villages that we're working with fabricated in this favela by Copa Roca, which is a women's sewing collective where women who live in the slum areas make money by sewing. They produced the textiles, and these women use the textiles. And these women have a lot of family members here, because people are moving from the north of Brazil to the south to try to find work, and they have a lot of family ties. So it's a really intense and emotional thing to bring the maker communities of energy with the user communities together. This is a little complicated, but we can quickly touch on this. So this is how it works. There is the sun, which is, remember, our equal partner. There's Luz Portátil, the solar textiles. And then there are all sorts of local industries, sustainable fishing, there's organic vegetables, beekeeping, and so forth. And people can, with a USB, charge their cell phone, and they can travel to Santarém, and they can download any of these free open source softwares to their phone. So they don't have the internet, but they can transport themselves to the internet so that they can connect with the internet. And what this means is that these small-scale producers, like, for example, this woman who has an organic garden and she sells produce, she can connect with the market, she can understand about prices, she can get better deals for her produce, her organic produce, and it's really kind of a game changer. This woman here is actually wearing the hat, is the president of ANA. I had the privilege to meet many presidents in these small villages, and she's a beekeeper. So you see her taking pictures to demonstrate the hives that she's made so that she can get a grant called the Bolsa Verde, green grant from the government by time stamping, really simple things, but time stamping these photos, GPS locating these photos, and using Panoramica to show where her hives are. And then this is sort of an interesting thing. We actually used MIT's Map Knitter software, which is a free software that you can download on your phone. And you take your phone, yep, that's a phone, and you take a kite, and you turn on the app and hoist it up with a kite, and you can get aerial, really high-resolution aerial maps. And that's super important politically for these small communities because they cannot own their land vis-a-vis the Brazilian government, even though this land has been theirs for thousands of years, because they don't have a map of it. So hiring a plane and hiring a cartographer is prohibitive, but these aerial views do work. And Google Earth picks where it looks. And it doesn't look too carefully in the Amazon. It looks very carefully in Boston, Dallas, but not so much at the Amazon. So these are really high-resolution photos, and politically that's been important. So we've been working with 13 different river communities at the junction of these two rivers. This is the Tapajos here, a little hard to see, and this is the Arapoints here. Oh, I'm sorry, this is the Arapoints here, and that's the Tapajos, which is a big part of the Amazon. And it's, pretty big responsibility. You feel a responsibility, to try to make sure everything is right and to test and to prototype and to try to improve all the time. This is sort of like a bunch of people, most of the people in one village that we're working with. So we can actually, for the first time, allow people to move in the traditional ways that they do move through the forest and along the rivers and have light and have the ability to communicate with a mobile phone. This is the first instance that I know of where that is happening. I want to conclude with two projects that I've never shown before, so bear with me. They have to do with plants, both of them. We have a very strong relationship with plants, not just houseplants, but we're a civilization that's basically based on the ability to have agriculture. And so we've been cohabitating with plants for a long time. And this project, which is about to break ground, is a botany research center called Global Flora. It recently won a Holcim Design Excellence Award for sustainability. It's a living building challenge project, which means it's got a very high standard of environmental responsibility, almost impossible to achieve. But we will try to make this be net zero water and net zero energy. We're working with Bureau Happold, Anthropology, David Small. Our contractor is Turner Construction. They're on board. They're building it. So they've been advising us on this. And Wellesley College is a very old and prominent women's college. And Margaret Ferguson, who first founded this collection of plants and the first greenhouses, had this kind of amazing idea that women should listen to plants. And I don't know what this person is doing here, but she actually is listening to a plant. And that, rather than thinking about that as sort of an absurdity, but we thought, well, how could we listen to plants? What do plants have to tell us? How could we, in our media, actually listen to what they're saying? And so we developed a platform with Global Flora whereby locally you access the Global Flora collection, which is like a conservatory. You can think about it as a museum for plants. All of these neighbors can walk, so there's adjacency. There are buses that connect to, there are like 24 different school programs that work with Global Flora. It connects to Boston via T and bus. So it connects locally, but all of these are just a few samplings of the kinds of research that are going on all around the world with these plants. So what our job was in programming was to try to imagine these scenarios whereby, for example, inside the greenhouse, someone could collect data from sensors about a mangrove tree that was growing in the greenhouse in Global Flora, and at the same time, somebody else who's planting mangroves in another country could share that data online, could actually understand exactly the temperature, the soil conditions, the amount of nitrites, et cetera, that were particular with that, so that the collection could be expanded to support research really around the world, to become truly global. That was the mission that we developed with Wellesley College. These are the old greenhouses here. They're more than 150 years old, and they're falling apart. And this is the global flora transformation. So we're using ETFE, which is a very thin, very optically clear plastic material. We're curving this from east to west to maximize the sun. There's a dry biome in this end of the project, and there's a wet biome in this end of the project. And in here, there's a temperate biome, which is really like all of Wellesley. That temperate biome contains one tree, the Durant camellia tree. And that tree was given 150 years ago to Wellesley College, and it grows in this pavilion, which can open during certain weeks of the year. So this is a clearer way to see the model, and what's unusual about this, you'll notice, is that we've lofted the section. So the lower plants are in the dry house, and then it gets taller and taller, and the crest moves in plan. So this is a kind of a three-dimensional lofting, and then we're using the earth as it naturally falls down the slope with Andrew Pogon. We're designing a topographical greenhouse with a bridge over to this mezzanine. So in plan here, this is the Durant camellia pavilion that will open. It just contains that 150-year-old tree, and that tree can live to be 400 years old, so it's really a teenager. You can have a kind of a path through, and you can then take a bridge up through the palms and canopies to the mezzanine, and then proceed down through the mangrove area, and then work your way back up the topography and out in this plan. So this is a view. You can see how those doors in the pavilion will pivot open, and this is ETFE, so it's super light material. You can do that. And this is all passive design, and it is net zero energy. And what's cool about that, I think, is that if you can do this in New England, you could do it almost anywhere, because it does get cold and it does get very hot and humid in New England. So we do this through a big, thick gabion wall filled with rocks that absorbs the heat. We're working with Transolar on this, and through greenhouse shades that capture that heat and lock it in when we want to radiate that back. This is a section view. You can see the topography, the various different ways in which the ground plane is folding up. And yes, we make material boards just like you do. These are our material boards, and all of our materials, including the ETFE from Foil Tech, it's actually fabricated within, it's fabricated right here in New York, so fairly close to the state of Massachusetts there. And looking from the mezzanine, what we imagine it's like, looking back across the bridge to the greenhouse. And then in our weather, it's kind of nice to come when it's snowing and to kind of like sense the presence of this thing on campus. So the last project I wanted to show you is a new project that we're doing at MIT. It's received a lot of news lately. And really it's about living plants, but more fundamentally it's about living with plants. This is called Nanobionic Plant Infrastructure, which is kind of a nerdy MIT name. But basically what we're doing here is my colleague Michael Strano and I are developing and prototyping urban lighting that will be ambient, that is plants. So it's kind of crazy to think about, but if you think about that world where there is no difference between technology and nature, this would be one instantiation of it. So a glowing plant, you might think, how's that possible? But if you watch this video, it's going to move from winter to spring, and you'll see all the temperate, there they go, all the temperate forests are going to start glowing. So this is a machine eye. It's a satellite seeing this glowing, but plants fluoresce. They fluoresce all the time. Your household plants, your trees in your backyard, they all glow Problem is, we can't see that part of the spectrum. The satellite eye can because it's a machine eye, but we can't. So plants already glow. Just so that if you take away one thing, I want you to know that. This is a carbon nanotube, a nanostructure. They're teeny tiny. Nanoscale is extremely small. And being carbon, it can blend with other carbon life forms, and it can shift the electricity that's inside the plant, because plants are an incredible technology already. They're a platform for technology that's amazing. They produce their own energy far more efficiently than any solar textile we could possibly imagine. They are adapted to dry and wet areas. They're very hardy, wild-growing plants are. They're resilient. They've adapted through millennia of evolution. And so what Michael is doing is developing new techniques to take a number of coenzymes that are at the nanoscale, carbon nanoscale, and introduce them to plants, either by pressurizing them or by immersing them into a bath. And he works with spinach, arugula, and cress and other leafy green plants. This is a biomedical carbon, so that you can eat it and you can compost it at the end of life. So have some spinach. Here's a test of one leaf glowing, and it is pretty bright. It is a small leaf, but if you take it very close to a book, you can actually make out some text. It's certainly not a street light by any means, but this is very early on. So we've received a Bose grant, which is a very generous grant to develop this. And we are working on mechanisms to understand the biochemical reactions between the carbon nanotubes and the plant itself. And what's amazing is that Xiang, the PhD student who's working with Michael on this, has actually already categorized on-off mechanisms, so that there are ways in which the plant can speak with other things in the environment, for example, levels of light and so forth, to turn the visible glowing on or off, which is pretty crazy to think about. There was a recent paper in nanotechnology on this, and a lot of news. If you look up MIT glowing plant, you will find it. And this is the pressurization chamber. So here now, in the air, the carbon nanofibers are being introduced into the leaves. So this is our project. How do we scale this? How do we think about this? What could this be good for? And how do we enter into a new and more caring relationship with plants? Because this is not a genetically modified plant. I want to be really clear about that. This is a plant that when it dies, it dies. It dies because a human kills it, or it comes to the end of its natural life, and then its visible glowing will also die. So if we want ambient urban plant infrastructure, we have to take care of these plants. We have to nurture them. And we have many years of doing that, a whole history of doing that. And my research group in the architecture department and in urban design is looking into what the implications of this might be. So I'll leave you with this last slide, which is the plants. These are the spinach plants, illuminating a couple of pages of Paradise Lost. So thank you very much for your patience. Thank you.